Okay, so in this video on atomic structure, we're looking at isotopes and a lot of the other keywords that are basically foundation words that you need to know in order to be able to do this topic properly. What do we know already? Well, we've got the atom. The atom has a nucleus which contains the positive protons and the neutral or no charge neutrons. Around that, we've got the electrons orbiting in shells. When an electron absorbs energy, it will move up an energy level, and when it moves down an energy level, it will give out electromagnetic radiation of an energy equal to the step that is jumped down. One of the things that got glossed over a little bit in the process of discussing the development of the atom and the atomic model was what makes each element unique and its own element. Now, Dalton had already put the idea out there that these elements were all different types of atom. The question is, what made them different? Why were they different? All that Dalton had to work on was the idea that these elements, these different materials, had different chemical properties, and at that time they had managed to determine rough approximate atomic masses for a lot of these different elements. Mendeleev didn't have anything more than that to work on, and he's famous for having created the periodic table by leaving gaps for elements that had not yet been discovered. His task was made more difficult by the idea that the atomic masses didn't go up in just a linear fashion. It didn't go 1, 2, 3, 4, 5, 6, 7 like the other properties of the atoms, which we'll be discussing shortly. The discovery of electrons by J.J. Thomson and the proton a little bit later on than that actually allowed things to take shape. And when Niels Bohr developed the idea of the electrons existing in shells, it was possible to then identify that these groups that exist within the periodic table had the same number of electrons in their outer shell. And by understanding how those shells get built up, and by understanding about now the discovery of the proton, they were able to determine that each element is defined by the number of protons in its nucleus, or the atomic number. So carbon, for example, will always have 6, helium will always have 2, lithium will have 3, nitrogen 7, and so on and so forth, all the way through the periodic table. There's an issue I think we also need to discuss about this. What do these words all have in common? Plom, plomo, jumbo, and blei. I don't think I've said the last one right, but never mind, we'll worry about that later. Well, simply put, they're all lead. But they're all lead in different languages. So the scientific community needs to be able to communicate accurately which element it's talking about in any given time or any given circumstance. Now, you know from your chemistry we have the periodic table, so let's use that as our solution. All the symbols and all the atoms on the periodic table tell us about that element. We've got the chemical symbol, which is always a capital letter, and sometimes there's a lowercase letter following it, but it is always at least one capital letter with sometimes a lowercase letter to represent the element itself. Now, that letter and symbol regularly are taken from their names. However, in the case of lead, it's taken more from its Latin name, which was plumum, which is why you've got the P and the B. You've got the atomic number, which is the number of protons in the nucleus, and fundamentally, that's the key thing for identifying the element itself. That atomic number and that chemical symbol, if I have either of those, I know exactly which element I'm dealing with. I know exactly how many protons there are in that nucleus. On top of that, we have the atomic mass, which is the total number of protons and neutrons in that nucleus. So if I want to find just the number of neutrons, I've got to subtract the atomic number from the atomic mass. Bit of a challenge for you. Spot the difference. Well, it's not really that much of a challenge when you break it down. They're both silver. They've both got 47 protons. Silver 107, or Ag 107, has 60 neutrons in the nucleus. Ag109 has 62 neutrons in the nucleus. They are both isotopes of silver. Now there's that word, isotope. It's one of the key words you need to be comfortable and competent with its use of. You need to be able to accurately define it. It regularly appears in the exam question. So let's do this. Isotopes have the same number of protons, as I mentioned in the previous slide. So silver, Ag, always has 47 protons, but they always have different numbers of neutrons. Same atomic number, different mass number. All the elements have isotopes. Literally every single element, even hydrogen, has isotopes, right, where there are neutrons attached to those protons inside the nucleus. Right? Some of them are unstable. But what does unstable mean? Well, an unstable nucleus will undergo nuclear decay in order to become more stable. The word unstable itself should be bringing into your mind images of things falling over or things not necessarily being able to stand up on their own. In the case of a nucleus, it means that the configuration of protons and neutrons in that nucleus can't stick around. It's going to have to do something to change to become more stable. Sometimes it can be as simple as a neutron being emitted. So in the case of beryllium-13, it's got more neutrons than the stable beryllium-12. So what it does, or a more stable version of beryllium-12, so what it does is it simply just emits one of those neutrons, right, and it becomes a much more stable isotope of the same element. Another option is that it emits ionizing radiation in order to become more stable. Now there's three forms of ionizing radiation you need to know about, but the key thing you need to be aware of is that ionizing radiation causes other atoms to become charged, or ions, by causing the atom specifically to lose electrons. The three types of nuclear ionizing radiation we're going to talk about are alpha, beta and gamma. And alpha and beta, as I mentioned before, are names that were coined by Rutherford in his research of this topic. In summary, for what we've talked about in this video, the number of protons in the atom dictate what the element is. The atomic number is the name for the number of protons within the given element. The mass number is the total number of protons and neutrons for that particular atom, and that can vary. The chemical symbol is the letter we use to identify the element. An isotope has the same atomic number but different mass number, and that's the kind of question that can appear as explain what an isotope is. What are the similarities and differences between two different atoms? Same number of protons, different number of neutrons is the kind of things you're going to have to be using in those statements. An unstable isotope can undergo nuclear decay. One option is a neutron can be emitted from the nucleus and it becomes a lighter, more stable isotope. The other options are that it gives out ionizing radiation from that nucleus, and there's going to be 3 separate videos on alpha, beta and gamma radiation to follow this one.